Hello, random math, non-elementary integrals part 2. Today we're working with the integral from e to the x over x dx. So this integral has a non-elementary solution because it cannot be defined in an infinite number of algebraic terms. But we're just going to be finding the integral anyway in its infinite form. So again, like we did in the last video, we're going to replace e to the x with its Taylor series. And so in order to solve this integral, we're actually going to calculate the integral from a to b. And then we're going to derive the indefinite integral from that. So we have the integral from a to b of 1 over x times the sum from n equals 0 to infinity of x to the n over n factorial dx. This 1 over x is x to the power of -1. So we can, and because it multiplies with the x inside here, we can add the exponents and it'll give us the integral from a to b of the sum from n equals 0 to infinity of x to the n minus 1 over n factorial dx. Again, like we did in the last video, we have to prove that the sum is uniformly convergent so that we can swap the sum and the integral signs. So let's do it. Let's do it the exact same way. So f sub n of x is going to equal our function inside the sum, which is x to the n minus 1 over n factorial. Then we're going to take the absolute value of each side. So f sub n of x, and the absolute value of that is equal to, because we're taking the sum from n equals 0 to infinity, n is positive, therefore n factorial is guaranteed to be positive, so we can kind of push the absolute value sign onto the numerator. And then this power can also be left out. So we're doing the absolute value of x to the n minus 1 over n factorial. And then let the absolute value of x be less than or equal to something, a. So the absolute value of f sub n of x is going to be less than or equal to, because we're basically kind of theorizing the maximum value of x, a to the n minus 1. And then you take the series of each side. And because this converges to, e to the a over a, and that means that f sub n of x is uniformly and absolutely convergent. Therefore, it's safe to say that we can swap the integral and summation operations. This gives us the sum from n equals 0 to infinity of the integral from a to b of x to the n minus 1 over n factorial dx. The division of n factorial is not in terms of x, so we can kind of pull that out. So now we have the sum from n equals 0 to infinity of 1 over n factorial times the integral from a to b of x to the n minus 1 dx. And then we use the power rule to evaluate the integral. So it's x to the n minus 1 plus 1 over n minus 1 plus 1, which is just, and because the 1's cancel out, it becomes x to the n over n evaluated from a to b, which is b to the n minus a to the n over n. Now it gives us the sum from n equals 0 to infinity of b to the n minus a to the n over n times n factorial. There's an issue though. If we just take the first term of the partial sum, you get b to the 0 minus a to the 0 over 0 times 0 factorial, which is 1. And that's 1 minus 1 over 0, which is 0 over 0. That's an indeterminate form. Very unfortunate, but there's a solution. And that solution is to take the limit as n approaches 0 of the function. So we have the limit as n approaches 0 of b to the n minus a to the n over n times n factorial. To shorten up this video, many people are going to be mad at me, but I love El Hopital's rule. I don't care what y'all say. I prefer it over anything so much. I love El Hopital's rule. And so we're going to use it because when we input 0 in this function, we just get 0 over 0 in indeterminate form. So it's valid to use El Hopital's rule here. Because we're taking the limit as n approaches 0, we're going to be taking derivatives with respect to n. The derivative of b to the n is just b to the n times the natural log of b. Same thing goes for a to the n, so minus a to the n ln of a, and then divide. How do we take the derivative of n times n factorial? Well, just treat them like two separate functions and use the product rule. The derivative of n is 1, so this becomes n factorial, and then you're going to add n times the derivative of n factorial, which is gamma prime of n plus 1, but we don't got to worry about that. We'll just call it n factorial prime. And now we can input 0. So this is equal to b to the 0 ln b minus a to the 0 ln a over 1 plus 1 times 1 prime. And remember that the derivative of a constant is always 0. So this term completely goes away. And also because we're left with 1 on the denominator and we're dividing by 1, this entire fraction goes away and we're just left with the numerator. We can assume that b to the 0 is 1. Y'all listen to me. 0 to the 0 is not equal to 1. That's just my opinion. I don't care. You can never change it. 0 to the 0 is not equal to 1. Fight me. For general cases, b to the 0 is going to be 1 and a to the 0 is going to be 1. So these go away. And you're just left with the natural log of b minus the natural log of a. And that is going to be our first term, ln b minus ln a plus the sum from n equals 1 to infinity. Because we already have this first term, the n equals 0 term is gone, so we just have to take the sum from n equals 1 to infinity. And then you just write the same function as before, b to the n minus a to the n over n times n factorial. And that is our definite integral. Now we're going to solve for the indefinite integral. First thing I want to do is I want to split this sum into two. Future me, sorry, I forgot to add the factor of n. So in the sum area, we have the sum from n equals 1 to infinity of b to the n over n times n factorial minus a to the n over n times n factorial. You get ln b minus ln a plus the sum from n equals 1 to infinity of b to the n over n factorial minus the sum from n equals 1 to infinity of a to the n over n times n factorial. That's a mouthful, sorry. And so now we're going to rearrange it so that the terms with b are first and the terms with a are last. And with this rearrangement, you should be able to notice something from the fundamental theorem of calculus, and it's that the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F of x is the indefinite integral of f of x. Over here is the function with inputted b, and then you're going to be subtracting the function with inputted a. And so if this is just the function, and so if this is just the indefinite integral with b plugged in, then just replace everything that says b with x, and then we'll be good. And so finally, we solved it. The integral of e to the x over x dx is equal to the natural log of x plus the sum from n equals 1 to infinity of x to the n over n times n factorial. And outside of everything, don't forget plus c. Thank you for watching. I'll see you guys on the next part of non-elementary integrals. Goodbye.